let's see. You could certainly use Pnp transistors. For an LED driver, it would be like this. Something like this would work. This is your LED, this is still the collector, this is RB. Now for this to turn on, the input needs to go low. Because this has to go low to get that 0.7 volt diode drop there. And when this is low, you'd have 4.3 across RB. You would use that then to determine the base resistance. You'd make sure that that's high enough. In this case, since we're using it as a switch, to turn on. And then when it's on, again, this drop is about 0.1, 0.2 volts. And so you'd have 4.9 volts here. If you take 2 volts there, that you can figure out the collector current you need. So it's similar. We tend not to use P-channel or Pnp transistors. They're not as available. They're actually a little more difficult to manufacture than NPNs, and they're also slower. Okay, so in a lot of applications, you can use either NPN or Pnp. But I don't really know of any advantages to using a Pnp transistor over an NPN. The majority carriers in NPN transistors are electrons, which are actually faster than holes. They have a higher mobility, if you remember that from electronics. So NPN transistors will turn on, turn off a little bit more quickly than the equivalent Pnp. There are some occasions you need them, and there are certain complementary circuits, a push-pull amplifier that uses both, and there you have to have them, but we don't use them that often because they're not used as often. So, I mean, that's why all the electronics books are typically written just showing you primarily how to use N-channel MOSFETs, NPN transistors instead of Pnp. So is there anything else on any of that? Okay, I'll give you another opportunity to submit questions in a couple weeks. So you certainly don't have to wait for a couple weeks to ask those types of questions. Whoever was struggling with the hex to bit, we've been doing that for a while now. Please come and see me if you're struggling with something like that. Finite state machines, or I'll use the abbreviation FSM. So these are an abstraction, a model that we can use to solve a lot of problems that we typically encounter with embedded systems or robotics. Matter of fact, you could have used like a finite state machine model for the 2 projects we've had so far. Anytime where you have the problem involves a transition from one state to another. It could be one LED going on or off, depending on switches. So a finite. Did you just talk about finite state machines in 254? You heard the term at all? Some of you are saying yes, some of you are saying no. Okay, depended on who you had, I don't know, or how good your memory is. So a finite state machine, we have states and state transitions. You may remember creating state diagrams. So we'll review that very briefly. You also have the input, the transitions depend on inputs. And then there are the outputs. There are 2 types of state machines that They're classified on, the classification depends on how the outputs are set. In a more finite state machine, the outputs depend on the current state. In a merely finite state machine, the outputs are a function of or depend on the current state and the inputs. And you can use actually either for all finite state machine problems. One may be slightly simpler than the other. So the general notation for a more finite state machine, there's a state name, and here you want to be a little more descriptive than state A. You know, it might be initialization or drive forward or something like that. And then here in the more, we indicate the output this circle represents a state. So in a more finite state machine, the output only depends on the state. Now here, this may be going to a display. It may be setting a particular port. It may be, you know, setting the display and turning a motor on. So there could be multiple outputs. And then here, we're allowing our state also to actually wait a minimum amount of time before it transitions. So the wait time might be 0, in which case you're monitoring the inputs all the time, or it might be infinite, that you would wait here forever. And then, you know, similarly, we would have another state. Now I'm gonna say we've just got a single input here. And, you know, so after 30 seconds, we check that input. If it's 1, we transition to state B. If after 30 seconds, we check that input and it's 0, we're going to stay in state A. And similarly, and you'll see, we'll look at some hopefully practical problems where the problem solution requires that you set up these states appropriately. There's no one way to do this. And an input of 0, when we're in state B, we transition back to A. So this is what's called a more finite state machine. You can tell it's a more finite state machine because the outputs are labeled in the state itself. Now, a merely state machine, the outputs are actually in the transitions. And usually with a slash. So this is input slash output. Okay, I guess I didn't label the input up here. So with the merely finite state machine, if we're in state A, after 30 seconds, we check the input. If it's a 1, we transition to B, and I guess for equivalence, we output a 0, 0, 0. If we're in B, we stay in B, you know, with a 1. But if we're in B and we transition back to A, if the input is a 0, we set the output to 1, 2, 3. And then similarly here, we stay in state A with a 0 and keep the output at 1, 2, 3. So these are roughly equivalent state machines, kind of do the same thing, set the output appropriately. So I'm going to give you some time to actually come up with a simple state diagram here for a vending machine. I'll call this back up earlier, but probably have to turn it off. So you always need to define your inputs and outputs. So for the inputs, let's say we've got a coin reader, a coin counter, something, and then we've got a keypad where the user can select the item. And we're gonna work on the type of vending machine here that's got the candy and the drill. Okay, like the one down here where you push the button and a particular motor turns on, there's like a spiral coil and that ejects the candy. As opposed to, like the Coke machines are a little more complicated. They've got a couple different motors to. So the outputs are a display. And then let's say we've got motors. We'll say we've got 40 different solenoids or motors or something that we've got to activate. So our candy machine is going to allow us to select 40 different items. So now is the state definition part. This is usually the hardest part. You want to think like your vending machine. Okay, so that vending machine is sitting down there now, waiting for someone to walk up to it. What do we want to call that state? So what? Well, let's give it a more descriptive name. Idle. Now, we're not going, I'm just kind of trying to come up with the state names at this point instead of coming up with the state diagram. How do we go out of the idle state? What happens? Someone inserts a coin. So that will bring us out of the idle state into, what do we want to call that state? How about this collection? And then, you're probably never going to do this right the first time. You'll see that it's relative, once you get the finite state machine defined and implemented in software, it's easy to modify. It's easy to go back and add additional states. But we'll try and keep it fairly simple now. What other states might we have?
There's not enough. I didn't receive enough money, so it has to return.
How do we know that? It's still kind of what transition, how does it know whether we don't receive enough? So here we're inserting points in the slot. That's typically what happens. Then what happens after the user makes a selection? So then it would go into some, I don't know, verification maybe at that point. We could verification to check to see if the user's got enough money. If they didn't insert enough money, I think we can probably just drop back into the collection state and ask for more money. If they did, we'll go to the vend. Okay, so the next thing would be our state transition diagram, idle. You know, our output to the display. So it probably just says insert coin, right? And then actually, we're going to wait there forever. We're not going to transition until our input here is you know, coin is inserted. Now, what happens there physically, you know, I don't know. There's some sort of sensor that indicates that a coin is dropped, or a weight sensor, you know, a light sensor that detects the coin, or there's some mechanism that actually counts the coins for us. And then we go into what we call a collection. Now, I think we'll stay in the collection state as long as we're getting coins, right? And at this point, probably our display, our output is how much money's been inserted so far. And we're going to wait here until there's an input transition. So finish this up. I'll give you a few minutes, 5-10 minutes to do this with, I'm not putting specific inputs here, but you know, keypad is our other input. And things are pretty loosely defined at this point. You know, we'll go into the verification. You know, it could say 80 cents on the display, and every item's $1.50. But you know, when it says 80, the user actually presses the keypad. That would transition from the collection to the verification. And then, you know, with the verification, and it looks like we may actually possibly need other states. Like if we if we don't have enough money, maybe we go back to collection. That might be the option. So let's say that's false, I guess. So the user keys in an item, 2 digits, and then we're in the verification. If there's enough money, we vend. If there's not, we go back to collection. The other state we probably want is like some change return state as well, right? We don't, and then that would actually be another output to open up return the change to the user. Then, and here, I don't know, we may just actually show, here in the display, I'll just put hash symbols to indicate that now we're showing the selection. And if we've got enough money, this is actually, a 0 wait time state. Once we enter that verification, we have somewhere a table of the actual item cost. And then in the vending, we probably still continue to show the item, but now also we would activate the motor corresponding to that. I would guess there's some maybe wait time here, 10 seconds while that motor is activated. And then I guess unconditionally, we're always going to come back into the idle state, maybe something like that. Again, it might be at least a first stab at this implementation of a vending machine. Probably, if we sat down and thought about it, we might want to define additional states. The next step would also, to get into the design of the coin collection system a little bit more, and also the keypad, what kind of inputs we're getting from the keypad. I want to go through, he has a fairly explicit example in the textbook. It's a fairly simple system. But we'll go look at the state diagram, the states, and look at the software implementation. It's actually simpler than the vending machine. It's a stoplight controller at an intersection of 2 one-way streets. There's no turning arrows even or anything like that. Just so he has here actually 2 inputs, ports 5.1, 5.0. He's got traffic sensors at the intersection to detect if a car is there waiting on the light. And then there's 2 traffic lights, so red, yellow, green. So he uses port 4 for that, pins 0 through 5. And I'll try to recreate his picture here. Of the intersection. Red, yellow, green. Red, yellow, green. And he actually has so pins 0, 1, and 2 are connected to the red, yellow, green. I guess this is southbound traffic. We've got a sensor here that detects. So this is an input. Notice the direction of the arrow. So we've got a sensor there that detects if there's car waiting on that southbound car waiting on that traffic light to turn green. And similarly, we have a sensor here waiting on this stoplight, perhaps, waiting on it to turn green. And then corresponding those three output pins control that red, yellow, green outlet or light. Now I'm going to follow what he has in the book. So he calls the states go in, which means the traffic's actually southbound, in my opinion, but he calls it go in and wait in. It's the north-south light. And when go in, you want the green on in and the red on eastbound, and then the ports. And so red here, so that's 1, 0, 0, and then 0, 0, 1. Okay, everyone see that? Assuming that a 1 turns on that corresponding light. So we want the red light to be on, so it's 1, 0, 0, and the green light to be on here, so 0, 0, 1. And then we could the other state he had, he's got actually just 2 more states, wait in, which is yellow north and red east. And so that's still 1, 0, 0, but now 0, 1, 0. In my opinion, he actually needs a stop in, where both would be red for usually for a second or so, but he omits that state. The only other 2 states he has, I think it's just an effort to simplify, is a go east on the east-west stoplight. So that's 0, 0, 1, 1, 0, 0, because we want the other one to be red. So this is green, east, red, north, and finally we want a yellow, east, red, north. And so that's wait, east. Yellow, so 0, 1, 0, 0, 1, 0, and then 1, 0, 0. So these are actually our outputs. So, and we can use the Moore machine here, because the output depends on the current state. And I think it's probably wise to have probably another stop-in state and another stop-e state. You wouldn't want just a general stop state, because you have to remember where you're coming from and where you're going. If you just went to a stop where both lights were red, you wouldn't know whether to go to a go in or a go e next. So I think you need 2 more states there in general. So And here's his state diagram. So we go in, and so our output is from that table over there. And we're going to wait there for 30 seconds. And again, one of the advantages of the finite state machine implementation, it's easy to modify all this stuff. We just go in and change the 30 in one place to 60, and it's automatically updated. Okay? And it's easy to find where we need to make the change. And the wait and or the caution, we're going to wait there for 5 seconds. Now the transition here, we're going to transition if we have, so our inputs are, I think in this order, this is high if we've got someone waiting at the north-south intersection. This is high if we've got someone waiting at the east-west. So we're going to transition if we've got anyone waiting at the east-west, regardless of whether anyone's waiting at the north-south. Now, so the other two states, and you could argue with this, would be the 0, 0 and the 1, 0. The 1, 0, understand, if there is no east-west traffic and you've got north-south traffic, you want to keep that light green. But I would argue, that after 30 seconds, if there's no north traffic, you probably want to change the light anyway, for pedestrians or bikes or whatever, or just so that the light cycles. Okay, it doesn't get stuck here, or if that sensor breaks and you're stuck there with that light forever. Ideally, if the sensors break, it would still go through some sort of cycle, I think. And then we transition, once we're in the wait, once we turn our north-south yellow, we always go, the next state would be turning the east-west green, regardless of the inputs at that point. I've never seen a traffic light go from green to yellow and back to green, right? It's always green, yellow, red, and the other intersections. So regardless of what the inputs are. And then in this state, we're going to have the east-west green, the north-south would be red. And similarly here for 30 seconds, and then wait, E0, 1, 0, 1, 0, 0, 5, and we transition here. We'll stay in this state. So I would say the 0, 0s ought to go here and here, and that would just stay if it's 0, 1 or 1, 0 up there. And then again, after the wait here, we make this transition always. 0, 1, 1. And this would be a more finite state machine. So the next step is how do you actually implement this in software? So you want some sort of data structure, struct that we talked about last time is actually ideal for this. You could put those structs into an array or into some sort of linked list. A linked list implementation is fairly common, but he puts them into an array here. This is probably, you know, a much more complicated problem than anything we've done to this point with our program. But if you look at his software implementation here of this finite state machine is pretty simple. There's not a lot of code involved. So he does, for convenience, define a sensor, just keyword as P5N, just for shorthand notation, to kind of remind you that you're reading your north, south, east, west traffic sensors, and defines light to be P4 out. Don't have to do that. You can just use P4 out everywhere. And then here's his struct that defines the corresponds to a state. So part of this is what's the output. So here, what are we going to set our 6 lights to? And then another part is how long we're going to wait in this state. And then the next part is actually, it's an array of 4 pointers that point to the next possible state. Now, there is no transition from go in to go E or wait E. Okay, so for go in, we're only in go in or wait in. Okay. But in the general implementation, and you can see that here, the first state is the go in state. And if it's 0, 0, we're going to stay in go in. If it's 0, 1, we're going to the wait in. If it's 1, 0, or 2, go in. And if it's 1, 1, we transition into the wait in. So this is the basic struct. It's got what our output is, how long we're going to wait, and an array of 4 elements. These are all pointers that show where we're going to go to next, what our next state is, depending on, we've got 2 input bits, depending on what those 2 inputs are. And so the output here, notice it's conveniently expressed in hexadecimal. So 2, 1, 2, 2, 0, what is that? B, and 1, 4. Is that actually? Yeah. Oh, I was off. 0C instead of 0B. Okay. And then these are the weights. The timing routine he uses is the 10 millisecond routine that we've already got defined. So 3,010 milliseconds would be 30 seconds. So a big part of this is actually setting up these data structures. Now here he's put them in an array. There's actually no need in this case to define these as pointers to the next element, to the next state element in the array. You could just use array indices here, and that's probably how I would do it. Is that, you know, my go in state is my 0 element. I'm either going to go into the 0 or 1. And so I would actually just fill these with the corresponding 0, 1, 0, 1 to indicate the index of the next state in the array. He does it with pointers. But the code is fairly simple. This is all the initialization stuff. Okay. And we've got a pointer here that's pointing to, actually, this should be initialized, and it's not. It should be the address of FSM 0. We'll start out in that initial state. Okay. Actually, he has defined convenient notation as that pointer is actually just defined as go in. So more simply, we just define that as go in. But if you'll notice what happens, he sets the lights from looks in that data struct, gets the output value, ORs that with the lights or the 3F or just the 5 bits that we want to change in that output port. So this is going to mask off the other 3 bits, so we don't change those. And then OR them in with this value that just changes the lower 5 bits. And then we wait for the prescribed amount of time that's in the structure. And then we read the sensors, the 2 bits. And then based on that input value, you know, it's either 0, 0, 0, 1, 1, 0, or 1, 1. We transition to the next state. So we update the pointer, and we just go around and do that over and over again. So, you know, depending on what the inputs are, we can take any one of these steps in this state diagram. You have to think about this code. It's in the textbook. I'll post it on the website so that you can look at it. But you might want to think about using finite state machine for subsequent projects. I may require you to do the next one actually. That is a finite state machine. And again, it will probably be turning on the LEDs in a more complicated order. Actually, I might have you just go back and do that first project, but using a state machine so you can see how simple, hopefully, it is. But we'll see. Any questions about that? The other thing I want to mention briefly is dynamic memory allocation. So if we need an array, but we don't know really how many elements we're going to store, we need to store in the array. You know, maybe it's reading values, you know, when our system starts up from, you know, over the internet or across some serial interface from another microcontroller or from an A to D converter, and we're putting these values in the array. The array grows. We don't really know what the maximum size of the array is. So your only choice there is to allocate more memory than you need. Now, we don't have a lot of memory on these microcontrollers. What is it? I think it's 64 meg. It's a lot compared to what used to be, you know, the first PC actually had far less than a megabyte in it. So I think the first PC they came out with was like 320 kilobytes of RAM, which you could upgrade to 640 kilobytes of RAM, so under a megabyte. But this thing has 64 megabytes of RAM, 256 kilobytes of program memory. So these little microcontrollers have a lot more memory, a lot more power actually than the first IBM PC, which costs thousands of dollars, I think. So we could allocate more memory than we need, or alternatively, you can use dynamic memory allocation, where we declare a pointer. Now notice I haven't assigned this pointer to anything. I haven't initialized it. I could set it equal to array, but with dynamic memory allocation, by the way, if this is defined inside a function, this would be defined on the stack. The space would be defined on the stack. RAM is actually split up into 2 areas. There's the stack, and then there's the rest. It's called the heap. So we use malloc to return memory from the heap, to set aside memory for us that's not going to be used for anything else. So it's setting it aside for us. Now malloc returns it's a void star type pointer. So we have to convert it to the right type of address. Okay, so this is a cast. This is what does that for you, keeps the compiler happy. And then we have to indicate the number of bytes that we want to allocate from the heap. So with dynamic memory allocation, this doesn't have to be a fixed number. You know, maybe you're going to need 50 integers. So typically, you know, this could be a variable. N would have to be set before we call this. Then it would be typically, you would do it like this, size of int. Size of int is, we have to pass here the number of bytes. So you could put 4 times n here if you knew on this machine that an n took up 4 bytes. But you know, if it's a char array, it'd be size of char. If it's a short array, it'd be size of short. If it's an array of pointers, it'd be an array of int star pointers. This would then initialize array p. You could then use array p just like your array. Okay. And then this would put that data value into that location in the array. And when you get done with the array, you can also free it. And that's really simple. You just there's a routine called free, and then you just pass it the pointer. The only other thing that you need to know is these are, to use these are in the standard lib.h header, free and malloc. So on Wednesday, we'll talk about, I promise we're gonna, in the next chapter, we're gonna look at actually using those little LCD displays, get a little fancier output. And so before we do that, we have to talk about 2-dimensional arrays, because LCD is actually is a 2-dimensional array. So we'll talk about that on Wednesday, and then that'll finish up the material.
How long did it take?